Hello and welcome to Trigonometry for Dummies. I hope you can get something out of this video. Let's start with the Radial Survey. What is a Radial Survey? Let's say you're on a football field. You've been tasked with estimating the perimeter and the area of the field. All you have is a compass and a tape measure, not long enough to measure the whole perimeter, but long enough to stretch over half of the field. We'll start by standing in the center of the field. This point will be called O. Facing true north, you have a friend walk to the edge of the field with the tape measure and measure the distance to be 30 meters. You then turn so your bearing is 60 degrees from true north and measure the distance 45 meters. At 110, the distance is 40 meters, 190, the distance is 20 meters, and finally at 280, the distance is 28. We can display these relationships in the table like this. Let's first label each point, starting from A, which is true north, and ascending the alphabet clockwise, till E. After drawing these out, we can see that they can be closed to create a shape called a convex hole. This is a jagged, simple replica of the field, which we can easily find the perimeter and the area. To find the area and outer edges, we'll need the angle of each inner segment. These can be calculated by subtracting the smaller bearings from their adjacent larger bearings. So the angle AOB is equal to the bearing of B minus the bearing of A, or 60 degrees minus 0 degrees, 60 degrees. The same thing goes for the rest. C minus B, which is 60 minus 110, which is 50. And so on with D minus C, E minus D, and for the last one, it's just 360 minus E. We can split this convex hole into 5 different triangles and calculate their individual area and outer edge to get the whole field's area and perimeter. Let's start with the brown triangle, AOB. We can see we have 2 adjacent sides and their angle from each other. You may recognize that in this case we can use the cosine rule to calculate the remaining edge length. Using the equation a squared equals b squared plus c squared minus 2bc cos a, and substituting our values, we get a squared equals 30 squared plus 45 squared minus 2 times 30 times 45 times the cos of 60 degrees, which solves out to be 37.9. We can solve this for the rest of the triangles and get the outer edges of each, which add up to the perimeter. For the edge DE, the angle DOE is actually 90 degrees, so it's a right triangle, so we can just use Pythagoras' theorem. A little bit of an explanation here is that the cosine of 90 degrees is equal to 0, which renders the whole component 2 times 20 times 28 times cos of 90 to be equal to 0. So subtracting it makes no difference from the equation. We can get the perimeter from the sum of each of these edge lengths, which is 189.1 meters. The area can be solved using the area of a triangle equation for each triangle. A equals half BH. However, as an altitude is not provided, we'll need to use the trigonometric version. A equals half times AB times sine of C. So for each triangle, A equals half AB times sine C. The total area is the sum of these results, which is equal to 2,361.5 meters squared. How does triangulation work? In surveying, sometimes it's impossible to get a distance from something because it's inaccessible by a tape measure, or such a long distance it wouldn't be practical to measure normally. Luckily, in this case, trigonometry works in our favor. Let's say we're trying to measure the width of a river. We obviously don't want to measure using a tape measure, as we could lose it in the strong currents, or even lose ourselves. Instead, we notice a rock placed on the other side of the river. Lining ourselves up with it, so we're directly across the river from it, we move 10 meters to our left and measure the angle from where we were in the first place to where the rock is, and we measure that to be 60 degrees. We now have enough information to find the distance from the first point to the rock. Let's first label these points to clear this up. The point we started at is A, the point we moved to is B, and the point where the rock is C. The width of the river, so from A to C, is x, and because we aligned ourselves with the rock, the angle A is 90 degrees, making this a right triangle and simplifying the problem. We can use simple trigonometry, first looking at SOHCAHTOA. We can see that the defined angle, from the defined angle, we're given the adjacent side and we're looking for the opposite side. So we'll be using opposite over adjacent or tangent. So the tan of 60 degrees is equal to the opposite, which is x, over the adjacent, which is 10. So it's tan 60 equals x over 10. Then we just multiply both sides by 10. So x is 10 times tan of 60, and we get x is 17.3 meters. Another example is if you want to measure the height of a tree, you can use the exact same principle. You move exactly 10 meters from the tree and measure the angle to be 45 degrees. I'll leave you to pause the video and try this one out for yourself. In this particular case, you may have noticed that the tan of 45 degrees is 1. So the height of the tree is the same as the distance you moved, which is 10 meters. Which also makes this an isosceles triangle, so the other angle is 45 degrees. But why is tan of 45 degrees equal to 1? Let's take a look at a different concept of trigonometry to find out. Let's draw a circle on a Cartesian plane. Its radius is 1. So the point on its far right coordinate is 1, 0. The top is 0, 1. The left is -1, 0. And the bottom is 0, -1. If we draw a line from the center to anywhere on the circle, we know that its length is 1. What about the coordinates of where the line intersects with the circle, though? Well, as in many geometry problems, we can create an imaginary triangle to help. You can see that the two other lines we've created are in fact the x and the y coordinates of the point, because we know that their distance from the origin on the x and y values is the distance of the point from the origin on the x and the y values. Now let's say we've been given the angle of this line from the positive x-axis, and that goes counterclockwise. We'll just call that theta. Now let's use our knowledge of trigonometric ratios to figure out the x and y values. We'll start by using SOHCAHTOA, starting with sine, which is equal to the opposite over the hypotenuse, which we can see is our y value over our radius. And we know that our radius is 1, so we know it's just y over 1, or just y. Similarly, cos is the adjacent side over the hypotenuse, or the x over 1, just x. So the x value is cos of theta, and the y value is sine of theta. This is important because no matter what angle we choose, this is true with a unit circle. Even with angles larger than 90, which are impossible on a right angle triangle, it still works. The thing with this concept is it is true for any angle, and is repeating. So if you go past 360, it just loops around. So sine of 90 is equal to 1. The y-axis on the line, which is 90 degrees, is 1. And if you do another full loop, another 360 degrees, that brings it to the sine of 450 degrees. It is also equal to 1. So it loops around. Now let's try to define tangent, or tan, in the unit circle. Our definition of tan is that it's equal to opposite over adjacent. And we know from what we've just explained that the opposite of this triangle is equal to the height, the y, or the sine of theta, and the adjacent is equal to the x, the cos of theta. So sine theta over cos theta. the y over the x. So tan theta is sine theta over cos theta. Rise over run. Now this gives us the gradient of the line. And the reason that's so important is that at a 45-degree angle, if you have a line going at 45 degrees, it rises the same amount that it runs. So the rise over run is, let's say, 5 over 5 or 10 over 10. Doesn't matter what number, anything divided by itself is equal to 1. So that's why the tan of 45 degrees is 1. Let's do a little more fun of an explanation to end the video. This one's on 3D trigonometry. Let's say you're a Mongol warrior in 1274. You've just launched an all-out attack on Japan, and as a barbaric and awfully intelligent person that you are, you want to burn down all the Japanese flags in the town you've just conquered. There's a flag in the middle of a pond you want to burn, but you can't swim, so you need to put a torch on a long stick to burn it. You're also pretty bad at estimating distances, but you want to get it perfect to impress the Khan. You also can't hold a long torch at an angle, because that would be way too heavy for even a warrior like yourself. You're looking for the height of the flagpole, so you can push a wagon into the pond and the torch hopefully reaches the flag to burn it. We'll start by getting some measurements. You can't get the distance to the flagpole to use a normal triangulation because you can't swim. So you use a little device that you put together to get the angle from the ground when you're facing north toward the flagpole to the flagpole. Then you move 10 meters so you're facing east towards the flagpole and measure the angle there. And these angles turn out to be 33 degrees from facing north and 40 degrees from facing east. Now it's time to grab your book and quill and do some trigonometry. Connecting the dots we got our measurements from, we make 3 triangles, which are all right angled. We can draw these out separately to make it easier. We'll also label these N, E, F, G for north, east, flag, and ground. We'll also label the height of the flag as lowercase h. Each of these triangles has one piece of information, but not enough for us to easily get the height of the flag. Now let's look at this northern triangle, NFG. The angle, FNG, is 33 degrees, and we can define the flag's height if we have the distance from it to the viewing spot. So we'll call that side NG. Looking back at SOHCAHTOA, we notice that we want the tangent of our angle. So therefore tan 33 degrees is opposite over adjacent, or h over ng. Let's try to get the length ng, which by multiplying both sides by ng divided by tan 33, we get ng is h over tan 33 degrees. Similarly, the other edge on the other triangle is equal to h over tan of 40 degrees. So the same thing, just a different angle. Now, using the trusty old Pythagoras theorem, we can assume that the square of these two sides added together is 10 meters. So if we lay it out like this, h squared divided by tan squared of 33 degrees plus h squared divided by tan squared of 40 degrees is equal to 10 squared, which you can factorize to h squared times, in brackets, 1 over tan squared of 33 degrees plus 1 over tan squared of 40 degrees, which is equal to 10 squared. And rearranging for h, we get h squared is equal to 10 squared divided by, in brackets, 1 over tan squared of 33 degrees plus 1 over tan squared of 40 degrees. And then we can just square root to get h equals 10 divided by the square root of 1 over tan squared of 33 degrees plus 1 over the tan squared of 40 degrees. And we can plug this into our abacus, and we now know that the height of the flagpole is roughly 9.4 meters. Thank you so much for watching, and hopefully you got something out of the video.